Okay, first and foremost, I'm going to kind of go through this unit like we did in class, kind of chronologically. I'm going to start with dissolving processes, but I'm going to jump into colligative properties here as well. Dissolving processes are how something dissolves, and a lot of you struggled with this on the quiz. We have two processes for dissolving. I'm spelling them wrong, though. The first one's dissociation, and the second one's molecular hydration. Okay? Dissociation is for ionic compounds. Molecular hydration is for molecular compounds. That means covalent bonds. Okay? Ionic compounds, when they dissolve, they dissociate. That means they fall apart into ions. So here's an example. Mg3PO4 2. When that dissolves in water, it's going to turn into 3Mg plus, 2 plus. This is the charge, it's its oxidation state from your periodic table. And the 3 comes from right here, the subscript, okay? And PO4 is phosphate, it's a polyatomic ion. I'm going to have 2 phosphate ions, and they have a charge of 3 minus. This is what's floating around in an ionic solution, not this, okay? Not your Mg3PO4 2. It falls apart into ions. That's why it's an electrolyte. That means it conducts electricity because you have free-floating charged particles. Molecular hydration, let's look at methanol. There's no metal and there's no polyatomic ion. They're all of those are covalent bonds. Just stays together. It just becomes surrounded by the water molecules and turns into an aqueous solution. Because there's no free-floating charged particles, this is a non-electrolyte. Because of this, when we look at colligative properties, what that means, excuse me, a colligative property means that the boiling point of a solution is higher than the pure solvent, and the freezing point of a solution is lower than a pure solvent. So it's boiling point elevation and freezing point depression, okay? This depends on concentration of molecules only. Not molecules, but particles, okay? The more concentrated, the greater the effect, okay? That means a lower freezing point and a higher boiling point. The greater the concentration, the greater the effect. So something like that's an electrolyte, something that dissociates into ions, is going to have a greater effect. I'm going to say a greater colligative effect than something that doesn't, okay? I put in 1 methanol, I get 1 methanol out, okay? I put in 1 magnesium phosphate, I get 3 magnesiums and 2 phosphates. So I get a total of 5 particles. So inherently, if I have the same concentration of the 2 of these, the one that has the more dissolved particles is going to have a greater colligative effect. So NaCl has a less of a colligative effect than CaCl2, which has less of a colligative effect than AlCl3. Okay? Because NaCl breaks apart into 2, Na plus and Cl minus. CaCl2 breaks apart into 3, Ca2 plus and 2 Cl minuses. And AlCl3 breaks into 4, so it's going to have the greatest effect. Okay? That's basically your dissolving processes. We'll get back into this a little bit when we talk about ionic equations. Okay, saturation in table G. Table G, things you need to know. You need to know that it's there, okay? This is solubility and this is temp. Solubility is going to depend on temperature, pressure, for gases only. Gases are the ones that pressure matters, and nature of solvent, okay? What I mean here is like dissolves like. That means that polar goes with polar and ionic, and nonpolar goes with nonpolar. So nonpolar solutes will dissolve way better in nonpolar solvents, and polar solutes and ionic solutes will dissolve way better in polar or ionic solvents. That is the concept of, and I'll put it on the bottom here, like dissolves like. We saw this in class when I did the hexanes in water. You saw the separation. And then I dissolved the iodine in it, and the iodine's nonpolar, and the hexane's nonpolar, so the iodine dissolved in the hexane, turned it that bright purple color, but it didn't dissolve in the water, so the water stayed colorless, okay? That's the concept there. So these are your solubility factors. This chart, table G, only shows you solubility versus temperature, so it's going to have a couple of saturation lines, and they're all going to go up at different rates. Okay, you might have one that goes down. Remember, if it goes down with temperature, it's a gas. A gas is most soluble at cold temperatures, just like you want a soda, right? So your gas is going to go down. Gas dissolved in a liquid. Your solids are going to increase with increasing temperature. Okay, these lines are saturation lines. Okay, so if we're looking here at solid number 1, this here is an unsaturated solution. This is a saturated solution. This is a supersaturated solution. It's above the line of solid S, solid 1 that I labeled there. This guy is more concentrated than this guy. This one's more dilute. Okay, this is more concentrated. Things you need to know is how to read this. If you're looking for an unsaturated solution, it's under the line. If you're looking for saturated, it's on the line. Additionally, you need to know that this is based on 100 grams of water. I will ask you about 50 grams. I will ask you about 200 grams. You just need to read the graph and then adjust your value. If I'm asking you about 50, you're going to divide it by 2. If I'm asking you about 100, you're going to keep it the same. If I'm asking about 200, you're going to double it. And most of you did very well on that on the quizzes. So I definitely go back and review your clicker quizzes for that case, okay? Let's look at this solid right here. I'm going to erase this so that it actually goes forward. Okay, let's look at this red line that I'm drawing. Let's say this is a saturation line. 2 red X's that I just drew, okay? The one that I'm circling in green is more concentrated than the one that I'm circling in black, okay? This one is more concentrated, even though it is less saturated. The saturation is relative based on the temperature and the solute. Concentration is more absolute. Okay, that's how you read table G. Use it to see your solubility trends. Okay, molarity, parts per million, and dilutions. Formulas are on table T. That's the back of your reference table. You got to look them up. You got to know what you're doing here, okay? You got to know which one to use. So, parts per million, we're going to start with that. Parts per million. That's grams of solute over grams of solution, not solvent, big difference, times 1 million. Please do not forget 1 million. That's a big number. I'm going to multiply your paycheck by 1 million. You're sure as heck going to notice it. Okay? Formulas on table T. So if I'm asking you to find parts per million, which I more than likely will, rather than the grams of solute or grams of solution, you're just going to write this down and then plug it in. If I said, what is the parts per million of 0.1 grams of oxygen dissolved in 1,000 grams of water, you could certainly do 1,000.2 here based on the way it's read, but because of the nature of these types of questions, just leave it as 1,000 times 1 million. Okay, plug this into your calculator, and you should get an answer. Make sure your answer makes sense. We've had a lot of weird algebra stuff going on recently, so just double check it. And then my answer is 100 parts per million. That's 100 of a million parts, 100 of them are due to the dissolved oxygen. That's different from molarity. Molarity is moles over liters, okay? Moles of solute over liters of solution. To make a solution, okay, you're going to make a solution, you will put in your solute first, and then you dilute you add solvent up to the amount that you're supposed to produce, okay? That's really important. Your molarity, you may be asked to find liters, you may be asked to find moles, you may be asked to find molarity. Molarity is concentration. This is just concentration. Let me change colors. If I'm solving for molarity, and I say I have 3 moles in 5 liters, that's just how you plug it in. And then your answer, which is 3/5, or 0.6, is in units of big capital M or molar, okay? If I have a 0.6 molar solution and I want to know how many liters are going to have 10 moles, here, cross multiply. So many kids struggle with solving for this on the bottom, okay? I know we hate algebra, but cross multiply here. So you get 10 equals 0.6V. And then you do 10 divided by 0.6, not the other way around, and you get 16.7 liters, okay? Molarity, liters matter. Must be liters. Okay? How do you know when to use molarity instead of the dilution formula, which is the formula that we learned the last day that we learned new things, okay? That's your last formula, your M1V1 equals M2V2, or MVVB equals MAVA. Either is fine. You'll know because in this formula, you're going to have 2 molarities or 2 volumes. So you've got to look at the question and read the question. What's the question actually asking you? Is it asking, is you changing a solution by adding more solvent, or are you actually just calculating the molarity or the concentration? You'll have 2 molarities or 2 volumes, and that's how you'll know to use the dilution formula. Okay? Formula. If you have moles and liters, you're going to use molarity. If you have a molarity and a volume and you're looking for moles, do not crowbar in molarity, your molarity formula into your, molarity into moles. Okay? Make sure you know which formula you're supposed to be using. Additionally, nowhere in this unit will you use 22.4. Absolutely not. Nowhere in this unit will you use 6.02 times 10 to the 23rd. That's how many things are in a mole. I don't care how many things. You will not use either of those. The only thing you might actually use is grams to moles. So if I say I have, I guess that weighs 40. If I have 20 grams of sodium hydroxide in 1 liter of solution, what's my molarity? I first have to convert grams to moles. So I have sodium hydroxide, so I need to look up its molar mass. Okay, I need to look up its molar mass. That's going to be the molar mass of sodium, which is 23, plus the molar mass of oxygen, plus the molar mass of hydrogen. That equals 40, okay? So I know that I'm looking at less than 1 mole, right? 20 is going to be less than 40. If a mole weighs 40, I should be about half a mole. And that's exactly what I get. I get 0.5 moles. Then I'm going to use my molarity formula up here and say I have 0.5 moles in 1 liter of solution, and my molarity is 0.5 molar, okay? Good. Your dilution formula is basically the same thing. You're going to plug and chug. I'll give you, how much 30 13.7 molar HCl to form 1 liter of 6 molar HCl. Okay, I have 2 molarities here, right? I've got 1 and 2, and that means that I've got to use my, forgot it now, I've got to use my dilution formula. So, my initial molarity is 13.7. How much of that do I need to use? That's my unknown. I'm going to form a liter of 6 molar. So, do the math here again. Do the math correctly, please. It's 6 divided by 13.7, not the other way around. And my volume is 4. Yes, that's fine. My volume is going to be 0.44 liters. So I use 0.44 liters of hydrochloric acid, and I dilute it up to 1 liter, and it will be 6 molar. Last thing we need to talk about, and I'm going to do it nice and quick because I know that you're probably getting tired of hearing me talk. I know I'm tired of talking. Net ionic equations. You will see two net ionic equations on your test tomorrow, okay? It'll look something like this. This is a common example that we've seen before. So, I'm going to give you something like that, and then you need to, I'm not going to do this one. You know why? Because it's too easy. Let's do something a little bit harder. Let's do sodium sulfate. So, you need to first predict the products, okay? This is a really important skill. You've got to know what you're doing. So, I'm going to rewrite the positive ones. Ooh. I'm going to, I've got silver and sodium, okay? I'm going to put my polyatomic ions, which I have 2 of them, in parentheses. So I know that if it's a number, if it's a subscript in the polyatomic ion, I keep it. If it's outside the polyatomic ion, it goes away. And then I switch their partners. So silver ends up with SO4. Sodium ends up with NO3. Now I've got to flip-flop them. So I've got to look up all their charges. So silver's +1, sulfate's -2, sodium's +1, nitrate's -1. Okay, so this is going to become 1, 1, and those go, that's all set. Okay, this one's going to become Ag2SO4. All right. Then I balance it. All righty, I need 2 of you and 2 of you. Last step is to look at table F and see what is insoluble. Insoluble. Sodium's always soluble, so that's going to be my key that silver sulfate is my precipitate. This is my solid. Okay? Now I've got to write the net ionic equation for this. So, I want to see who's playing in the game. The easiest way to do this, to write your net ionic equation, is to start with your product, which is Ag2SO4, draw the arrow, and then write the dissociation products of it. The dissociation products are what it falls apart into. So if this were to dissolve, it would fall apart into SO4, 2 minus, and Ag plus, but there's 2 of them, 2. Okay? Additionally, you could separate everything out. This would be Ag and NO3. This would be 2Na and SO4, 2 minus. This would be Na and NO3, and this would be stay together. Stays. Why does it stay together? Because it's solid. Okay? This is my net ionic equation. This is not supposed to be a 3. That's just an underline. This is my NIE, net ionic equation. Okay? Make sure your charges match. Does your charge balance? I have 2 times +2 minus 2 equals 0, so that's what I'm looking for, 0 on both sides. Does your mass balance? I have 2 silvers, 1 sulfate, 1 sulfate. Yes and yes, okay? Finally, your spectator ions. They're what's left, Okay, so who didn't dissolve? This guy didn't dissolve. This guy stayed aqueous, sodium nitrate. To split that into your ions, that's going to be Na plus and NO3 minus are your spectator ions. That means they don't take part in they don't play in the game, okay? Do your review packets. That will certainly help. What else did we talk about? Go over your clicker quizzes that we did for this unit. Make sure you see what you're doing there, and do some practice problems, and you're going to be fine. I have total faith in you.